Can you see my screen? Yes, yes,
yes, I can see you. How are you?
Okay. Whenever you can start the talk.
So you just start your presentation, so we can see you.
Okay, can I start then?
Yeah, sure.
Okay, so good morning everyone. Let me just okay, start here. So now it's better. So thanks for coming, and it's an honor to be here giving this talk. Let me just go this volume here because I can hear my voice. Okay, now it's good. So I would like to thank everyone for this invitation. And let's start. Today I'll talk about some our recent work that we focused on rainfall forecasts for Korea, and currently this work is under review for Journal of Hydrology. And as Professor said, my name is Carlos Lima. I'm Professor of Civil and Environmental Engineering at the University of Brasília. So I will start here. Okay. So some quick question for motivation. First of all, we want to improve daily rainfall forecast using statistical models. So how we can do that? Let's see. And we also want to consider the uncertainties in the parameters and probability of the rainfall forecast. We're going to build a model that proposes this things. And as well as how we can account persistence and large-scale climate information into the model. And finally, we want a model that we can easily adapt to real-time rainfall forecasts. Not only a model that we just test, but a model that we can say, okay, in the future we can use this model. It doesn't take so much time to, let's say, to converge or to estimate the parameters, so that we can use it for real-time rainfall forecasts. So basically, this is the motivation of our work. So let's see. We have a model for the daily rainfall forecasts. Okay, we will consider stochastic weather models that were originally developed for rainfall simulation, not forecast. Basically, it's a seasonally varying mixture of a Bernoulli distribution. The Bernoulli is for the rainfall occurrence, 0 or 1, basically, and a gamma distribution that's for the rainfall amount. That's a very, very common model we find for rainfall simulation. And in this model, we want the possibility to include endogenous predictors like the previous rainfall, as well as external predictors, like we can build some climate index, or can be even some climate forecast from weather models, so that we reduce bias and variance of the forecasts. And finally, we want to estimate the parameters of these models on the hierarchical Bayesian framework, so that we have a better understanding of the parameter uncertainties, as well as some reduction in these uncertainties, particularly for gauges with short records. That's the case in some regions, in many regions, I would say, of the world. And this is also very interesting because under this model, it supports the estimation of regional parameters. That's so that we can, let's say we have some engaged sites, there is no data, and we want to also provide forecasts for these regions. So that's our general idea of a model. So this is the basics of our model. We say that Y is the rainfall, and we model the rainfall occurrence as the probability of rainfall greater than some threshold. In our case, this threshold would be like 1 millimeter, but can be 0. So it will be like pi. This is the probability of rainfall as indexed by I is gauge, T is time. And when the rainfall is greater than this threshold, we assume a gamma distribution with shape parameter alpha, IT, and scale parameter beta, with I, here should be T, Okay, that's our basics of our model. If we employ the concept of generalized linear model, GLM models, we will have some link function G, okay, that links the probability of rainfall with some function of predictors X, okay, and also the expected value of Y for the rainfall amount, we will link with some predictors X, can be the same or not, it doesn't matter in this case. And our expected value can also be for the gamma distribution. It can be related to the shape and scale parameters using this relation here. So let's, in here we just use the canonical link functions. That's the logit link function for the rainfall occurrence, so that we have the log of pi over 1 minus pi equals to some linear function of predictors. This is just to make life easier. We use this linear function, can be other non-linear function, but let's say just for now that we have this link function here, or linear function, sorry. So we have x1 and x2, those are external predictors. I will show in just in a few seconds for you. And we have also y here with some time t prime, some previous time t time. So t prime is t minus tau. Tau is basically the lead time of the forecast. So this is the basics of our link function. And also for the average value of the rainfall amount, we have the canonical link function, that's the log function. Also another linear function of the same predictors. It doesn't need to be the same predictors, but here we consider the same predictors, x1 and x2. Those are external information, basically climate predictors. And we have also the y, that's the internal information, or endogenous information, that's the previous rainfall. The coefficients, we have a here, and here we have b. Those are different coefficients. So in the end, we have for the rainfall amount, y following a gamma distribution with shape parameter alpha. This is interesting because the shape now is constant. It just depends on the gauge sorry. It doesn't depend on time. But the scale parameter is alpha over mu. Mu, the mean now, it depends on time through this function here. So we can just use MLE estimates to obtain these parameters here. That's easy, relatively easy. There are tons of applications in the literature and also extensions for the rainfall simulation that use this kind of model. But we want to do something different. First, we want to build this model for rainfall forecast, not simulation, as well as we will estimate using a Bayesian framework, hierarchical Bayesian actually framework, so that for the rainfall occurrence we have this prior distribution for A, so that's a normal function of some average over the region. Basically, we are shrinking all the A's towards some common mean across the region. That's our assumption, okay? And we have some precision parameter tau that allows some variation, okay? And for the hyperparameters, these guys here, A bar j and tau aj, we just assume some uniform distribution because we don't have any prior information, okay? If on a code, we will just code as some normal with mean 0 and some very, very low precision or high variance. That's basically a uniform distribution. Same thing for tau. But just remember that for tau, it has to be greater than 0. We have a gamma distribution with these parameters. That's it mimics kind of uniform distribution, and it also eases the convergence. Okay, so for the rainfall amount, we have the shape parameter alpha I as following a log normal distribution because it has to be greater than 0. Also shrinking towards some common mean. We have some common mean over the domain. And B, the same thing, but it can be some normal distribution, it can be less than 0, and also shrinking towards some common mean. This is because now we are reducing the uncertainties of these parameters. We say, okay, gates that are close, they have some common parameter, basically. They have some common average parameter. And we can use these average parameters as regional estimators. That's another thing. As the region is not so large, we can assume just a simple average. And for the hyperpriors, we just assume uniform distributions, basically. Okay. So in the paper, I show all the likelihood function, the joint posterior distribution. I will not show here because I don't have enough time. So, but if you want to see, I can just show in the paper. So the full hierarchical Bayesian model, we use Monte Carlo Markov chain simulation to sample from the joint posterior distribution of the parameters, basically the likelihood times the prior and hyperpriors. We cannot just integrate this function. It's a little bit complex. We code everything in R, and here we use the JAX, okay? And the RJAX function in R, not bugs. I think JAX for this case is, it works pretty well. And we have a set of parameters for each month and for each lead time where it goes from 1 to 7 days. So in the end, we have 12 times 7 set of parameters. And the threshold is 1 millimeter. So data, rainfall and climate data. So we use 6 rainfall gates located in Korea, provided by KMA. That's the period, 1973 to 2019. Wind field data that we get from the reanalysis project and second car reanalysis project. And we focus on the low-level wind because it's more important for the moisture transport, especially at this daily scale. So, and then we extract the wind field over a domain that covers the entire Korean peninsula, so that in the end we have 30 grid points. So here's some results. All the results, they are in the paper. I'll just show some of them. I think the most important for you guys. Here's just the historical wind field. What we observed is for January, we have this pattern here. Here is Korea, okay? We have moisture, not moisture, but we have the wind. It's a kind, it's like from the Asian, it's coming from the Asian continent towards Korea. So it's, if you look at the meridional wind, meridional is the north-south wind, it's like, it's negative, so it's from north to south, okay? The zonal wind is like eastward. When you look at July, that's your summer map, we see that we have a different pattern. We have moisture, now it's moisture from the East China and Yellow Seas towards Korea, so that the meridional is like from south to north, it's positive. The zonal wind basically eastward is positive as it is in this case. This pattern is interesting for July, as you guys know more than me, is your main rainy season, and your dry season it's in January. So you can see clearly it's mostly related to the moisture transport from these regions. But also interesting is when you look at now just the average regional wind along the month, so the seasonal distribution, we can see that the average is positive during the summer months, so we have moisture from the Yellow and China Sea, but we have also negative vibes. So we have, it's just showing that you can have a suppress of moisture during the summertime. And as for the winter time, on average, the meridional wind is negative, so it's coming from the Asian continent, but you can also have some positive vibes, showing that you can have some moisture transport from the Yellow and China Seas, even during the winter time. So this is some basic explanation so that we say, okay, let's say if you can consider this as climate predictors. But another thing that's important is we cannot just take the average wind so that because we have different patterns of oscillations. When we apply physical component analysis just to the meridional wind, we see two different patterns. One is when we look at the loadings, a common pattern of oscillation. So all the values are positive. This explains 63% of the variance. And there is also a second pattern, a kind of seesaw pattern of oscillation. Positive loadings, negative loadings, that explains 21% of the variance. So it's interesting to use both patterns as predictors, not only the average, meridional of the region, but also both patterns. And let's see somehow these patterns are related to the rainfall amounts. Here I apply just the self-organizing maps to cluster the rainfall amounts, okay, for the entire region. We find these 6 different clusters. We see that cluster 3, there is no rainfall basically. Cluster 2 is here. We have like a little bit more rainfall over the region. Cluster 1, you have more rainfall, and so on. So that cluster 5 and 6, they have more rainfalls. And when we related these clusters to the PCs, what we observe is they are clearly related to the meridional wind. So that when the wind has the two components, they are low, almost negative values, you have low rainfall. As you increase the components, you also increase the rainfall over the region. Also, it's also more uniform over the region. And here is just some scatter plot and cross correlation functions showing this relation of rainfall and the wind factor. So, and then we use the wind factor in our model. I will just show here some cross-validate results. My time is like 60 minutes, I have to finish. So, here is the bias score. Basically, it's just the gain over the RMS mean score. So, what we observe here, when we use the baseline model 1, is just the climatology, just the average. Here, when we use the persistence, okay? Persistence, basically, I just consider as the previous rainfall as predicted. And we see that overall we have positive values, especially up to 3 days lead times. Okay, showing that our model is better, let's say, more steady than both models here, up to 3 days lead time, and even more. Let's get the rainfall rate. For the rainfall amount, use the well-known weekly skill score, okay? And again, up to 3 days lead time, we observed again up to 45, 50% of the weekly skill score. And our baseline model is just the climatology. Just some values of correlation skill. Just remember that this is cross-validated forecast, okay? I didn't use this data here to estimate the parameters. And we have correlations, average correlation from 0.45 up to 0.1. And finally, some example of forecast. For 1 daily times, we have 4 randomly chosen gates. So the correlation is around 0.5. Okay, we can see that the forecast more or less follow the observed patterns, the dots. And for 3 days lead time, we have a different pattern, we have a drop in the correlations, but still, when we consider the critical intervals, it knows most of the observations. So, this is some results, and just a summary, we obtain again up to 50% for these skills, magic skills, up to 3 days lead time. Beyond this one, the model structure that considers the uncertainty, it still favors the use of it over the climatology. We can include other predictors. For instance, we can use climate models. For example, climate models, they can be easily included in these models. So it's a step forward improving real-time forecasts for the region, for Korea, but it can also be applied to other places across the world. Okay? So, and finally, we acknowledge the support of the Advanced Water Management Research Program funded by the Ministry of Land, Infrastructure and Transport of the Korean government. Okay? And one more time, thank you guys, thank you, for this opportunity. And if I have time to answer questions, I'll be very happy. If not, you can always send me some email that I'll be very happy to answer. Okay? So, thank you.
Carlos, can you hear me? Hello?
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 Let me just...
Hello?
Hello, huh?
Can you hear me?
Just a second. Okay, now I can hear.
You didn't share your presentation, so we didn't, actually cannot see, your main results.
Okay, can you see my talk, my presentation?
Yeah. So can you share the last slide, so you can actually see the main results of your presentations.
The last slide, okay.
I mean, still we cannot see. Yeah.
This
Can you
one?
go? Yeah. Can you go up? Yes. So can you summarize your result again, because we cannot your slide actually.
I'm sorry, huh? I didn't hear you well.
Actually your slide doesn't show up. Okay.
Okay.
So anyway, I can understand your presentations. So I have one question for you. Okay.
Okay.
Actually we got the quite a bit good predictability for the 1 day forecasting, right? 1 day ahead forecasting.
Can you repeat, please?
The result is quite depend on the reason time, right?
Yes.
Can you hear me?
Yeah,
No?
just a little bit. There is some noise. You didn't see my last slides, huh? Or I'm just seeing here that you didn't see my slides?
Can you hear me? Okay.
Yes, I can hear.
The result is, the predictability of the rainfall forecast quite depends on the visit time, right? So we only get the good result. No?
Oh, you just saw the results?
이게 잘 안 되는 것 같은데. Okay, can you hear me again? No?
Yes, a little bit better because there is some noise.
Okay, let me I'm going to email you and then about your presentation. So maybe we can move on next speaker, because we're still quite tight time schedule.
Okay, you want me to talk again after the next speaker?
Yes.
Oh, okay. Because you didn't see my slides.
옮겨줘요. 프레젠테이션. 3번.
다른 사람들?
예, 이문수 교수님.
Thank you. Anyway.
이문수 교수님 계세요?
어디 계세요?
네, 저기. ES. 우 교수님.
네. Hello?
네. 예. 그 화면 좀 공유해 주실 수 있을까요?
Sure. Yeah, just a second.
그 두 번째 탭에 보시면 화면 공유 있을 건데.
Okay, I'll try. Could you see my slide?
Yes.
Okay, can I start?
목소리는 크게 해주세요.
잘 안 들리세요? How about now?
It's better, but still you should be.
In that case, just if I had better use my microphone. Hello?
Yes. Yes.
Can you hear me? It's better?
But still 좀더 크게 해주세요.
Oh. So how about it? It's not clear?
It's not clear.
Hello?
교수님.
네.
시작해도 될것 같습니다.
잘 들리세요? 아직 문제가 있나요? Hello? Can you hear me clearly? Not really?
잘 안 들려요.
요
오디오를 올려드릴까요?
왜 오디오 올려?
이것도 잘 안 들리세요?
네, 잠깐만요. 이게 문제가 아닌 것 같아요.
아까 외국인은 잘 들렸잖아요.
네, 컴퓨터 문제가.
이게 지금 맥시멈이거든요?
네. 잘 들어볼게요.
예.
잠시만. 이게 처음 해보는 거라 저희가 수치가 나와가지고. 차라리 줌이면 날 것 같아, 줌이 아니라서.
이게 줌이 아니나요?
줌이 아닌데.
이거 뭐죠?
구름이라는 건데.
구름?
교수님, 들리세요?
어떻게 시작할까요?
시작했는데 괜찮습니다.
예.
더 크게 들려요?
괜찮습니다.
좋네.
Good morning.
So
So I'm Shunim, now working for the Hong Kong University of Science and Technology. Before getting into the main subject, I'd better tell you, I'm not really an expert in hydrology field. I've been working on the dynamical downscaling using a real-time model and produce fine dynamic predictions in response to unique scenarios to understand the regional climate impact due to global warming. So today I would like to share some of the focus on precipitation from the climatologist. This is my first time presenting this conference. I have little information about the participants, so I don't know how much you are familiar with dynamical downscaling or real-time modeling. But I think it is safe to say that many of you are interested in utilizing reliable climate information in your own research. So I prepared this whole composed of two main parts. First, I'd like to share some evidence to demonstrate the benefit from high-resolution climate simulations. We all agree the accuracy of future climate information is critical to improving the reliability of a hydrological impact assessment because they are used as key input data. But I believe many of you know that detail climate data set important to precipitation data, but a significant body of hydrology modeling we still use global climate model in spite of fundamental skill yet. So as a recycling modeler, I feel like the value of dynamic now scaling seems to be rather underestimated. So it's a good chance for me to touch on this issue here, emphasizing what kind of value we can expect from the real-time modeling. Then I moved to the future climate change in Korea. I categorized the change pattern and identified the dominant modern verdict along the different level of warming. We have a general perception that models show more robust precipitation changes as global warming, the larger uncertainty. That might be true, but I'd like to argue that actually climate model and behave in a described way is so completely enough. So I'd like to share with you to convince this argument the part of this book. So first, what does the real climate model look like? This to overcome the limitation forced with the global climate model. This climate model is net in climate model of specific interest region, the high resolution. To better geographically diverse features in Korea, I developed non-nested downscaling the model domain covering East Asia and West domain of Korean Peninsula. So we could obtain very fine scale like 500 data over without tremendous cost. Uh, Here I introduce comparison with kilometer and calculations to demonstrate how higher resolution the improvement was captured prediction pattern over here. Actually, the factory heterogeneity topography pattern rather than, but this is water difference for our own precipitation. First, let's see somewhere meaning climatology in the last 20 years. Compared to pattern, kilometers seem to overactive middle in some 20 kilometers and
인터뷰 듣고 잘 들려요.
performance the special pattern and every mean. But please note that resolution no, not to resolution.
이렇게 스피커 조금 끊겨요.
Sorry?
No.
If you look in
Interannual variability after area averaging over Korea, it's hard to find significant difference between 20 kilometer and 5 kilometer simulations. Indeed, the blue color and red color lines are almost identical in this figure. So, what does that mean? Does this imply that the impact of a higher resolution is marginal? If yes, I had better change my research topic, right? But it's not really true. Before you reach such a wrong conclusion, I move to the next figure. This is the spatial distribution of annual maximum precipitation climatology. I pick up only one maximum value per year and make them average for 20 years. In this case, we can see better performance of 5 kilometer simulation in a more clear way. If we look into the frequency distribution of daily precipitation, not averaging any temporal dimension, then we can see quite a different performance across the model resolution. In this analysis, I also add the result from 75 kilometer reanalysis precipitation to clearly see some resolution effect. For the weak and moderate intensity, their differences are relatively small, but for the high intensity range, their behaviors are quite different. For example, coarse resolution that is used for driving forcing to run the regional climate model completely failed to capture extreme precipitation over 150 millimeter per day. And only 5-kilometer simulation red dot reach a maximum daily precipitation of 420 millimeter per day, which is much closer to the observational value. For better illustration, I try to compare the result after simply interpolating into the same grid system. In this box plot are generated using the daily precipitation above 95 percentile every year from the original output and its disaggregated or aggregated output. For example, for the comparison at 5-kilometer grid, 5-kilometer simulation indicated the original output, but 20-kilometer and 75-kilometer resolutions are disaggregated into the same 5-kilometer grid. So we can check whether the added value obtained from the high resolution is retained after spatial aggregation. If the added value can be found when upscaling to the coarse grid, but not vice versa, that is the effective way to demonstrate the benefit of physically downscaled high resolution simulation. So if we compare 5-kilometer output after aggregation to the 75-kilometer the resolution is last three the box plot, we can clearly see it preserves the improved ability to simulate high intensity precipitation. In contrast, the lower performance of coarse resolution output cannot be improved by simple spatial disaggregation. In addition to improvement of extreme precipitation, the added value of higher resolution can be also found in the representation of physical process. In climate model, total precipitation, that is one you use for your analysis mostly, is a result combining two different types of precipitation, so-called large-scale precipitation and convective precipitation. They are calculated in a totally different way in the climate model. And here I don't want to spend the time to explain the details about them, but I want to say that their different behavior is important for mechanism study. This bar graph indicates the ratio of convective precipitation in the summer month of individual year. Here, gray bar comes from trim satellite data, so considers as a true value. We can clearly see some systematic behavior between 5-kilometer and 20-kilometer simulations. Coarse grid largely overestimate the fraction of convective precipitation throughout the whole period. On the other hand, 5-kilometer resolution shows much improved partitioning of convective and large-scale precipitation, showing much closer value to the observed one. So even if mean precipitation shows a similar amount between 5-kilometer and 20-kilometer simulation, their behind combination is not the same at all. Some of you may thinking why this is important as long as we can get the right total precipitation. I agree, you don't need to care about such a details, but right partitioning plays an important role to establish the relationship between extreme precipitation and temperature. This graph presents the frequency of convective and large-scale precipitation as a function of temperature. In this graph, x-axis indicates the temperature, so we can see precipitation change along the temperature. First of all, let's see the simulated frequency of total precipitation along the different temperature line. Green dashed line here, and observed pattern is black dashed line. We can clearly see the green line from 5 kilometer simulation is much closer to the observed black dashed line. Much more striking feature come from the comparison of fraction change between all precipitation case and extreme 99% extreme precipitation is a solid line. There, please see is lower panel. Then you can see convective precipitation fraction from extreme and all precipitation event. Actually, the 5 kilometer simulation, in most of cases, convective precipitation is less than 50%, red dashed line here. But for extreme case, the fraction of convective precipitation can surpass large scale precipitation at temperature around 55, and their portion reach to the 75% around 20 air temperature range. Actually, this behavior is very similar to observational one. But 20 kilometer simulation does not capture such a behavior. It implies that dominant precipitation pattern along the different temperature range is very sensitive to the warmer temperature. That's the reason why the realistic partitioning has important implication for enhancing the reliability of future precipitation projection under global warming. Here, I shortly address the future precipitation change pattern generated from the downscaling result. In this study, our target precipitation is not really extreme precipitation. We select relatively moderate level of precipitation. So, because our attention mostly focus on the very extreme case, and extreme case shows relatively robust pattern under global warming, but moderate precipitation shows very mixed signal. So here, based on such a joint distribution between temperature and precipitation, we divide 4 different categories and see what happened in the future over the Korean Peninsula. Here I analyze the change pattern under 2 different levels of warming, 1.5 warming and 3 degree warming. Actually, I selected these 2 warming because 1.5 degree warming is some symbolic target after Paris Agreement, and 3 degree warming is expected to reach within 21st century if we allow the RSP 8.5 scenario. Under 1.5 degree warming, all 4 categories are emerging, even though category 4, which indicate intensity increase and frequency decrease, occupy considerable area. But under 3 degree warming, category 2 and category 3 are disappeared, and large part of category 4 are also converted into the category 1. Category 1 is corresponding to the both increase in intensity and frequency. Such a transition behavior of precipitation change can be explained by the change in precipitation characteristics in response to global warming. As an example, I randomly select 2 points and check their change pattern in the probability of future daily precipitation along the different intensity. We can clearly see the asymmetric response in higher and lower intensity range under 1.5 and 3 degree global warming. Their pattern, we can say their pattern quantitatively similar, but the gradient is much steeper in 3-degree warming rather than 1.5-degree warming. And such a less gradient under 1.5-degree warming make the probability transition shift to the more intense precipitation, like this figure. So if the warming level is strong enough and precipitation intensity is strong enough, then the change pattern are eventually converge to the category 1, characterized by increase in intensity and frequency. Due to time limitation, I skipped the summary also. I skipped a lot of the technical details. If you are interested in, you may find more details from these the publications. I stop here. Chairman, I stop here.
Hello?
Yeah,
Yeah,
you can
I can't hear you. So you finished your presentations? 발표 끝내셨냐고요?
Yes.
Yes.
네.
In fact, I finished it.
지금 방송 상태가 별로 안 좋아가지고 듣는 사람들이 좀 어려운 부분이 좀 있거든요, 교수님.
보셨나요?
슬라이드 봤습니다, 저희 봤고요. 제가 질문 하나 드려도 될까요? 아마 지금 물론 RCM 모델들이 계속 뭐 발전되고 있는 거에 대해서 다들 동감하고 하는데 교수님도 좋은 방향으로 설명을 해주셨잖아요, 그죠? 익스트림 밸류에 대해서 재현 효과나 이런 거에 대해 설명해 주셨는데 그럼에도 불구하고 여전히 저희가 수문학적인 관점에서 쓰는 데 있어서는 여전히 바이어스 커렉션이나 기타 등등의 여러 가지 포스트 프로세싱 필요하잖아요, 많은 경우에. 그죠? 그래서,
이거 한번 해볼까요?
네, 하세요. 대부분들이 한국 학생들이어서 일단은 괜찮습니다. 그래서 제가 질문을 일단 애들 좀 들으라고 말씀을 드렸던 거고, 그래서 이게 저희가 어느 정도 시점에서 이 리저널 크라임 모델이 특별한 포스트 프로세싱 없이 우리가 원하는 그런 워러시드 스케일을 쓸 수 있는 정도가 될 수 있으려면 어느 정도 기다려야 될까요?
그거는 다이어트라고 저는 생각하지 않거든요. 기본적으로 인풋 어세스 하시는 분들의 퍼센티지에 관한 문제라고 생각합니다. 많은 언제나 잘못 결과를 시하는 리저널 모델이 다이어트가 어쩔 수가 없는데 그 정도를 정부가 빠른 시간 안에는 없이 리저널 크라임을 가능하지 않다고 생각합니다. 하지만 바이어스 커렉션을 운영하는 하더라도 커렉션되는 메커니즘가 다르잖아요. 글로벌 바이어스 커렉션을 민 패턴에 대해서는 리저널과 패턴을 보여주지만 우리가 익스트림이나 공간적인 그런 포비언까지 완벽하지만 커렉션을 할 수 있지는 않거든요. 그런 측면에서 지금 리저널 크라임 모델을 사용할 수 있다고 생각하는 분을 추천드립니다. 왜냐하면 하나의 리저널 모델을 사용하는데 가장 크게 그림돌이 됐던 게 멀티플 다운스트리밍 리저널을 사용할 수 없다는 거였는데 요즘은 인터내셔널 콜라보레이션을 통해서 인터내셔널뿐만 아니라 국내에도 적어도 세 글로벌 모델에 대한 다운스케일링된 결과들이 퍼블릭에 오픈되고 있기 때문에 지금 당장 사용하는 분들은 펄섹션의 문제들이 바이어스를 언제쯤 특정한 레벨로 할 수 있냐는 문제가 아니라고 생각합니다.
네. 시간이 좀 별로 없어서 일단 여기서 마무리하고요. 네, 고생하셨습니다. 감사합니다. 쉐어했나요? Can you share the screen? 혜미야. 화면을 쉐어. 두 번째. 지금 백퍼라고 떴기 때문에. 맞아. 소리를 키워줘야 돼. 저쪽 소리를 내줘야 돼.
근데 저쪽에서 이거 마우스를 클릭해서 마이크를.
어떻게 된다고?
저쪽에서 마이크 여기 마이크 있잖아요. 저기 빨간색. 그걸 클릭하셔서 풀어야 돼요.
마이크를 지금 풀어줘야 돼. 지금 네가 음성으로 돼 있어. 거기 지금 거기 보면 괜찮아. 밑에 거기 참여자의 밑에 보면 이거 하나.
My name is Shishi. I'm a of Water Resources Engineering at the University of New South Wales in Sydney, Australia. Firstly, thank you for inviting me to deliver this talk that discusses some of the recent advances my research team and others have made in the whole space of forecasting. This is an area that we are quite passionate about and we have contributed a lot to. And this is an area that I have had a lot of help from several PhD students, many of whom are listed over here on my title. So basically, this talk is about forecasting rainfall across a range of timescales. So it starts with seasonal rainfall forecasting and then gets into the more challenging and more complex forecasting problems that we face at decadal or even longer timescales. And these timescales are becoming very important to us nowadays. So that is what my talk will focus on. Before I get started, let me just give you some background to this research. So forecasting of rainfall requires different forecasting techniques depending on the lead time of the forecast. If you're trying to predict the rainfall tomorrow, what is most important is the state of the climate today. So prediction is a matter of looking at the evolution of today's conditions at a lead time of 1 day. But if you're interested in assessing the rainfall in, say, 10 years or 20 years to get a ballpark idea about whether your area will have more rain or less rain in the future, then today's climate is not important. What matters is how the boundary conditions that define the climate, the greenhouse gas conditions that define the climate, might be evolving over the next 10 years. So let me just go over this again. The first box that I have here talks about weather forecasting, and this weather forecasting depends very much on the persistence from one day to the next day, and this prediction is often an empirical or a statistical model prediction, because all it needs to look at is what was the evolution of rain between today and tomorrow, and try to capture this evolution that we have seen in past records to form projections of the rainfall that you can expect to see in the coming future. But if you're looking at longer timescales, decadal or even century-ahead timescales, then what really matters is using a climate model. A climate model where you can change the boundary parameters of the climate. You can change the carbon dioxide concentration. You can change the greenhouse gas emissions into the future and see how these impact the whole evolution of the rainfall. But climate model predictions are not so simple to use, and the reason for that is that the rainfall in climate models is not very well simulated, which makes the whole idea of using climate model predictions for rainfall or water resources applications a little, let's say, disconcerting. I give you an example. This is from a very old paper that one of my students published many years ago, which shows the average rainfall patterns in Australia and how these patterns are simulated across 18 different GCMs. So you can see the same pattern. This is for one particular cell that is over here, a grid cell. One GCM might have a 50% simulation of the rainfall as compared to another GCM. And this kind of captures the type of uncertainty you're having, even though we are talking of annual averages here. So this is the millimeters per day of rainfall averaged over the entire record. So even in terms of averages, you have as much as 100% variation in these GCMs. And this was captured in a metric that we developed in this paper called the VCS metric, the Variable Convergence Score. Kind of gives you the skill score, the skill of simulating different variables by the GCM. Well, if you look at the skills are pretty high for temperature and pressure, but for rainfall, precipitation rate, the skill is barely 7 out of 100. And that is the